welcome to my YouTube channel. So here today we are going to be looking at work done on an incline. So we are going to look at many questions to equip us on what we need to know. So we are going to do all these questions. Now before that, let's discuss some terms. What is mechanical energy? So mechanical energy is defined as it is the sum of the potential energy. It is the sum of the potential energy and the kinetic energy. So therefore, the mechanical energy is given as adding the potential energy plus the kinetic energy, like that. So this is the formula for mechanical energy if you add those two. So now, if according to the law of conservation of mechanical energy, it states that the total energy of the system remains constant if only conservative forces act on the system. So we are saying that the total mechanical energy of a system remains constant if only conservative forces acts on the system. Like for example, the example of what we mean by this is this. Let's say the conservative force that we might have is gravity. So I'll explain what non-conservative forces are. If you have gravity like that, then if you have, let's say you are dropping a ball like that from a point, let's say from here, then this ball at this point, it will have its maximum maximum potential energy, because at this point this is the highest point, so this will be at its maximum potential energy. But for kinetic energy, at this point it will be equal to 0 because it's not moving. When it is released, when it is so when you add potential energy plus the kinetic energy here, since kinetic energy is equal to 0, it will give you a value. Let's plug in some values. Let's say the potential energy at this point is 40 joules. So let's say the kinetic energy here is 0 joules. So we are going to have 40 plus the 0 joules. We are going to have 40 joules, like that. So under the influence of gravity, let's say at the midpoint, the ball begins to gain the kinetic energy, and it will have half the amount of the potential energy at the midpoint. So at this point, the potential energy will also be half, because potential energy, remember, is equal to mgh. So if the height reduces by half, it means to say from 40 it will be 20 joules. Then likewise, even the kinetic energy will be able to gain as it is going down when it reaches the middle part. And if there are non-conservative forces only, such as gravity, then we have 20 joules. When you add 20 plus 40, you will have the mechanical energy to be equal to 40 joules even at this point. Then at the last point, just before it strikes the ground, you will find that your kinetic energy will be approximately 40 joules. Now potential energy at this point, the potential energy will be equal to 0 joules, because we know that the potential energy is equal to mgh. If the height is 0, it means to say it will more like destroy everything. So if we add the mechanical energy at this point, it will be equal to 40 joules, like that. So that is basically how that is done. So if the total mechanical advantage of a system remains constant if only conservative forces act on the system. So in terms of the word equation, that's why we say the mechanical energy is equal to the potential energy plus the kinetic energy, like that. So now if you look at this one, we have said that, so this is the mechanical energy like that. Now, what if there is a non-conservative force? Non-conservative force. So mostly non-conservative forces will result into the loss of energy or takes away work. Okay, mainly there will be a loss in energy. So now, as you can see, when the pole was falling, the energy is not necessarily that it's lost, it's being transferred from potential energy to kinetic energy. But there are non-conservative forces such as air resistance and, let's say, friction. So these tends to take away energy. Like, for example, if you have a surface like that, if you have something like this, then it is moving like that. So due to the fact that there is resistance here, there is the force of friction which opposes the motion, which will always be pointing in the opposite direction as to where this is going. So that force, as you may know, if you are rubbing something, sometimes if it's let's say a metal pan, it tends to produce sound. Sometimes you will find that there will also be the loss of heat like that. So due to these two factors, this is what we refer to as the non-conservative forces. They tend to more like take away energy like that. So that is what we basically mean by non-conservative forces. So if a non-conservative force is there, mechanical energy, or rather the work, since we are dealing with work, remember from our previous video we defined work to be the product of the force and the distance moved in the direction of the force. So before I explain this, let me just finish. So for work, if there is a non-conservative force, we say work done by a non-conservative force, work done by a non-conservative force, non-conservative, so NC. So what we just denote it is NC, work done by a non-conservative force, is equal to, should be equal to the change in the mechanical energy like that. Now remember, mechanical energy, so the work done by a non-conservative force is equal to the mechanical energy is equal to the kinetic energy plus the potential energy, but we have just included change like that. So PE here. So basically this is what we refer to as kinetic energy plus the change in the potential energy, which gives us a change is calculated by the final thing minus, that's how you calculate change, minus the initial, which will be KEO. Then we have plus the final potential energy minus the initial potential energy, which will be like this. So this is the formula of a work done by a non-conservative force. Don't forget this, we are going to use it. Then we also are going to be looking at the Work-Energy Theorem, which goes by the formula, the net work done, if you add all the works, it will be equal to the change in the kinetic energy. So if we have this thing, so as it is moving, so this is kinetic energy. So all the works, how it is moving from one side to the other, if you combine the work, do what the gravity is doing, what the normal force, what the force in the y is doing, what the force in the x, if you add all these works, they are the ones that cause motion. So that is what we refer to as work done net work is equal to the change in the kinetic energy. So that is basically what the work-energy theorem is. So the net work done, or the total work done, is equal to the change in the kinetic energy. With that said, let's solve some problems. Before that, let's recap on one thing that is very cardinal that we talked about last time. So if you have someone like that, then they are carrying a bucket. So this person, they are carrying a bucket on top of the hat. So they are carrying a bucket on top. As they are moving this side, this person is said to have not be doing any work because they are moving. Let's go back. They are moving in this direction. But the force is pointing downwards. So the force exerted on the bucket is down while the person is moving in this direction. So remember, force is the force. Sorry, work is the product of the force and the distance moved in the direction of the force. So this is basically what we have. Distance moved in the direction of the force, like that. So sometimes there will be need for you to attach the cos of theta, which is the angle between or rather the angle of elevation between the point where you are going and if two of them are parallel, the angle between two parallel lines. If you just hear the word parallel, just know that the angle you are using for the distance is 0 degrees. But that does not mean to say it might be different from what you will use on the force. This will make sense as we solve questions like that. So that is basically work. So if we look at our knowledge of dynamics, if you recall, if we have something like this, which is a lamp, without wasting time, let's say we have 30 degrees here, then here we have this. So in another video, I explained on how these angles were derived. So if you have a lamp like that, or rather if you have a box like that, if you draw like that, this will be your normal force. If you extend your normal force, this will be what you're going to call your mg cos of theta, like that. Then since this, due to the fact that it is sloping down, this box will always want to be going down. So this is as a result of a force. It won't want to go up unless a force is applied, but naturally it will be following gravity like that. So as you can see, this is the slope that is also facilitating gravity. So that's the force that you use for calculating the work done by gravity, which will be your force, which will be your, in this case, this will be your mg cos of, sorry, not cos, but sine of our theta, like that. So this is what we have, mg cos of theta. So if it is going down, automatically the friction should be going up like that. So if you're asked on the work done by gravity, you're going to look at what is the distance. What is the distance from here up to where the object is more like reaching. Then also you're going to consider the force, the frictional force, in that way. So that is what we are going to have. So we have talked about how this, and we are going to understand how it is used. So let's begin. So the question says a crate of mass 10 kg is pulled up a rough incline with the initial speed of 3 meters per second. The pulling force is 250 parallel to the incline. That means to say the angle between them is 0 degrees, which makes an angle of 30 degrees with the horizontal. So the pulling force is 250 newtons parallel to the incline, which makes an angle of 30 degrees with the horizontal. Then we are told that the coefficient of kinetic, so this is the incline, so it's 30 degrees. The coefficient of kinetic friction is 0.5 and the crate is pulled 5 meters. Then the first question says, how much work is done by the gravity? First see the diagram. So already if it's a rough incline, that means to say frictional force is present. So we are going to have something like this. So this is what we are generally going to have. Now what are we taught? We are taught that a crate of mass 10 kg is pulled up, meaning to say it's going up. So we can draw it down here to show where it's coming from, or we can even draw it like that. Then we are going to split. So same thing, down. If you want, you can even memorize at this point, but you can watch on how these were derived. So down here, it will be mg cos of theta. When you extend this, it will be, your opposite will be your normal force, like that. Downwards, this force will always be pointing downwards. It will be what you are going to be calling your mg cos sine, mg sine of our theta, like that. Now if that's the case, so remember we are told that a crate of 10 kg is pulled up a rough incline with a speed of 3 meters per second. So it's being pulled up, so it's going up. That means to say the frictional force will be opposing the motion. So that force that just wants to resist the motion is the frictional force, and it will be pointing in the opposite direction. So this force is the force which is 250 newtons is the one that will be pointing up, since it's the one that is pulling up the frictional force down, like that. Then one thing that you need to know, remember the gravity, it is following the slope. So this is what you are going to be using for you to calculate the gravity always. So work done by gravity, you are going to say work done by gravity will be equal to, you are going to say work done by gravity, so just Wg is equal to, we are going to have the force times the distance. So this distance, you are going to attach your cosine of theta. Now this theta is not the theta here, which is what angle is there, so the 30 degrees, no. So this theta is the relationship of how the distance, in terms of the distance. So for the, if you look at this one, cosine of theta for the gravity. Now remember, it is going up. So if it is going up, gravity pulls things down. So that means to say, if anything is going up, it shall be negative. Remember that knowledge that we learned in kinematics. So it shall be negative, like that. So therefore, knowing that the force that is assisting in gravity is your mg sine of theta, so you should know that that's the force that assists in gravity. We are going to say the F will be the force, this force that will be assisting gravity is our mg sine of our theta, like that. Then we are going to have times our distance, like that. This part you can even forget it to avoid confusion, but it's okay if you can say cos of. Remember, it is more like it is going up. So that means to say the cos that you can use is 180. Cos of 180 is the one that gives you -1. So we have, because already the gravity is acting down, but it is going up. So if these two are parallel, that means to say it's a straight line. Like for example, if you look at an object like this, it is going in this direction. The friction will be moving in the opposite direction. So the angle between that is 180. So each and every time there is more like a difference in the direction, then that will be 180 like that. So we are going to have, but if you can just add a negative here without even saying cos of 180, it will be easy. So we are going to say the work done by the gravity will be equal to what is our mass. So our mass is 10 kg. So we are going to say 10 kg times gravity is 9.8 newtons per kg times the sine of our theta is equal to, we have 30 degrees. So we are going to say 30 degrees, then we are going to say times the distance. So the distance, we just get the distance which it moved. We are told that the crate is put 5 meters, so we are going to have by 5. This gives us cosine of 180 is -1. So just as I said, if you know that principle, that as long as it is going up, the work done by gravity will be negative, because gravity pulls things down. So the work done by gravity will be equal to, we are going to have 10 by 9.8 by the sine of 30, then we have times our 5. What we are going to get is a negative 245 joules like that. So work is measured in joules. So this is basically how you calculate that. We are going to be conversant with these things. Then the next one says how much work is lost due to friction. So the work or the energy can be the work. So the work lost due to friction just calculates the work done by friction. So remember, in the previous video as well, we were saying that the work done by friction should be equal to the frictional force by the distance with the cosine of 180. Why 180? Because it will always be acting in the opposite direction like that. If we have T like this, if we have the force that is in this direction, the frictional force will be opposing the motion by pointing the other direction. So what we have from there is the frictional force. The frictional force we don't know. We also learned that the frictional force is equal to the coefficient of kinetic friction if it's moving times the normal force. So we are required to know the normal force in this case. So remember, our force is not at an angle. If our force, if it was like this, then there would be needs to be able to more like split this into components. The F cosine of let's say the angle, if it was 30 here, 30 degrees and all that, but we are not going to do that simply because that's not how it is. It's like this. We are told that they are parallel, they will never meet, and the angle between two parallel lines is equal to 0 like that. So with that said, we know to say, for us to calculate the frictional force, we have said that it will be the coefficient of kinetic friction times the normal force. Now knowing that from Newton's second law, the summation of forces, the normal forces in the y should be equal to 0. So we are going to have the normal force. So if you look at the diagram, the normal force is pointing up. This one is the parallel, mg cosine of theta. So if you look at your normal force, then minus the other one that is pointing in the other direction, which is your mg cos of theta, should be equal to 0 like that. So this gives us a value that is equivalent to, we have the normal force should be equal to mg cos of theta if this goes the other side, like that. So with that said, we are going to calculate the frictional force. So the frictional force, we have said that it is equal to mu k Fn, which will be mu k. Then where there is Fn, we are going to put our mg cos of theta, like that. So this is the frictional force, which we can replace or we can just put it there. So the work done by the friction should be equal to, we have said that the frictional force times the distance times the cosine of 180 degrees. So this gives us a value that will be equivalent to, we put this mu k mg cos of theta. So we take this whole thing, we replace, times the d cos of 180 is equal to -1, like that. So our mu k gives us a value. We have our mu k, which is equal to, let's grab this. Our mu k is equal to, according to this, we are told that our mu k is 0.5. That's the coefficient of kinetic friction. So we are going to say 0.5 times our mass, which is 10 kg, cos over the angle, which is 30 degrees, by d times -1. So multiplying everything, we are going to have 0.5 by 10. Then we have the cosine of distance moved. So the friction was moving throughout this whole thing. Where is it? So it was moving, it moved this whole thing. So it moved this whole thing. Therefore, that's its distance. So we don't overlook that. So that is basically what its distance is. So we have, what values do we have? Cosine of our 30, which will be 4.33. Then we have times, remember we have our d. What is our d here? Our d is equal to, the distance traveled was 5, so we are going to say 5, like that. 5 times -1. So if we multiply this by -5 by 4.33, this gives us a value that is equivalent to, it's mg. So mg, we have forgotten, very important, by g is 9.8, like that. So that's why we are even getting a smaller value. So 0.5 by our 10 by our 9.8 is 49 cosine of 30, which will give us a value of 0.866. Sorry, let's multiply, just pressing everything together. Distance 5 by -1. So pressing everything together, we have a 0.5 times 10 times 9.8. Then we have the cosine of 30. Then we have by our 5. So this gives us a negative value, since there is a -1 here, which makes sense for the work done by friction, which will be negative 212.18 joules. So that is how we do that. So we have found the work to be negative 212 joules. So this was the energy lost. So we can say, therefore, energy lost should be equal to, we have found it to be negative 212.18 joules. So this was for friction, and it is the energy that is lost. Then when we are told how much work is done by the 250 Newton force. So for the third one, work done by force. So work done by the force should be equal to its force times the distance times the cosine. Now remember, this force is applied parallel to the incline, meaning to say the incline and the force applied, this incline and the force applied. So this incline and the force applied, which is this one, they are more like they are parallel, meaning to say the angle between them is 0. So this is this cos attached to the distance is mainly for that approach. So we have our force like that. The work done by the force is equal to, we have the force, it's 250 newtons, then we have times our distance, which is equivalent to 5, like that, by the cos of 0. Cos of 0 is 1, so that we have our 250 by our 5, which will be equal to 1250 joules. So this is the work done by the force. The third one, which is saying that what is the change in the kinetic energy of the crate. If you remember, we said that the net work done should be equal to the change in the kinetic energy, which is what they want. So using the Work-Energy Theorem, that is what we get. Now, knowing that the net work done is equal to the work done by gravity plus the work done by the normal. Please, you don't put potential energy for the network, plus the work done by the friction plus the work done by the force. So these are the things that are making up the net work. So we are going to find the net work to be equal to what is our work done by gravity. So the work done by gravity was found to be equal to negative, because it was going up, negative 245. So we are going to put negative 245 joules, like that. Then we add plus our normal force. Now remember, this normal force is on the incline, like that. This incline is in such a way that things are just more like it is completely touching, and we know that the normal force goes up, but yes, it's elevating up, but it's not more like leaving this point of contact. So it's not doing that, it's not entering and leaving. So there is no work by the normal like that, because the contact is maintained throughout. So we are going to say plus our 0 joules plus the frictional force. In this case, we found the frictional force to be equal to negative 212 negative. So we are going to put our negative 212.18 joules. Then we have plus our work done by the force, which was this 1250 joules, which will give us the net work done should be equal to, we have the negative 245, then we have our minus 212.18, then we have plus our 1250. So this gives us a value that is equivalent to 790 2.82 joules like that. Now remember, we said that the net work done should be equal to the kinetic energy, the change in the kinetic energy. So the change in the kinetic energy, which was what they were asking for, what is the change in the kinetic energy of the crate? So the change, just leaving it here, so it will be equal to 792.82 joules should be equal to the change in the kinetic energy. So this is the answer that was required. Knowing that that is what we have gotten, then they asked us what is the speed of the crate being pulled 5 meters. So how do you calculate the speed? Provided that you already have this equation, no needs to waste time. So the change in kinetic energy is equal to, so we can have our change in the kinetic energy. So we have 792.82 joules should be equal to, we have the final kinetic energy. So this change can be final kinetic energy minus initial kinetic energy, which will be final kinetic energy is equal to half, kinetic energy is half mv final squared in this case, then we have minus half mv initial squared. So we have 792.82 joules, which gives us our half mass is also common, so we have half mass, then we have v final squared minus v initial squared, which will be 792.82 joules, which will give us 792.82 should be equal to 1/2. Then we have the mass. So the mass of the crate is 10 kg, so we are going to say 10 kg by 10 kg. Then our velocity final squared minus, are we given the initial velocity? So the initial velocity was 3 meters per second, so we use that. So we have 3 squared, don't forget about the squared. Then we have our 792.82 should be equal to half of 10 is 5. Then we have our v final squared minus 3 squared is 9, which when we divide 5, we divide 5 so that we can remain with this divided by 5 gives us 158.564 should be equal to, we have velocity final squared minus our 9 like that. So taking the 9 this side, it will be equal to 158.564 plus 9 should be equal to v final squared. So if we add plus our 9, we are going to get 167.564, which should be equal to velocity final squared. If we find the square root, this gives us a value that is equivalent to 12.945 meters per second should be equal to that is our velocity. So that is how you use that equation. So alternatively, you can say using the work done by a non-conservative force to be equal to the change in the mechanical energy like that. Now remember, non-conservative force, we might have friction. The non-conservative force, we might have the friction. We add with another non-conservative force. In this case, we can be able to add the force applied. So these are non-conservative forces. So non-conservative forces mostly will take away or add more force or energy to the system. Like for example, if you look at the frictional force tends to takes energy. That's one thing. The force is adding energy, Now this energy cannot directly be added to the potential energy. It's more like it cannot be converted to potential energy. So these are non-conservative forces. If you have it takes energy and also it is adding energy. So in this case, if you have a force applied, if you didn't have the force applied, then the non-conservative force can be frictional force. So we are going to say, remember, we have the frictional force plus the force applied should be equal to the mechanical energy should be equal to, we have the change in the kinetic energy plus the change in the potential energy. Now, how do we calculate change? We say kinetic energy final minus kinetic energy initial plus we have the change in potential energy is potential energy final minus the potential energy initial, like that. Then we have the frictional force plus the force applied, like that. So work, not just force. Work. So the work done by a non-conservative force. So we have the work done by a non-conservative force there, which gives us plus the work done by the force. It is not just the force, like that. So this is what we have. So we are going now to replace. So we are going to have the work done by the friction. According to this, we are going to have the value of work done by friction is equal to negative 212. So we are going to say negative 212.18 joules. Then we have plus the frictional force, the force applied, which is 1250 joules, should be equal to the final kinetic energy is given by half mv final squared minus half mv initial squared. Then we have plus the final potential energy, which is equal to mgh final. Now remember, this object started so it was moving up, so its initial potential energy at the bottom where the height is 0 is equal to 0. So we are going to put our potential energy there to be 0, our initial to be 0, because the height, remember, it's mgh, but if h is 0, that means to say the potential energy is 0. So we are going to have our value, which will be equal to, if we say negative 212.18 plus 1250, this will give us 1037.82, which should be equal to, we are going to replace our half, then the mass according to the question. Let me move this. According to the question, where are we? According to the question, our mass is equal to, we have 10 kg. So we are going to put our 10 kg like that. Then our velocity final, which we don't know, velocity final squared plus our half. Our mass is 10. So we multiply by 10 kg by velocity initial squared, which will be equal to the 3 squared. So we are subtracting here. Then we have plus our 10 by the gravity, which is 9.8. Now height, you need to be very careful. Let me create more space. So you need to be very careful on the height. So how do you account for the height? So it is very, very simple. What is this height? So we have been given the height of the lamp to be 5 meters. Now the work done by the potential energy is associated with the vertical height. So be careful. So when you're calculating the potential energy, the height is from down here to where it is and not how it has moved. So we have something like that. So this is how you have moved. This is we are only interested in the initial position and the final position in terms of the vertical height. That's how come when we look at a non-conservative force, you are going to be interested in what distance it has moved. But for a conservative force, you are just going to look at the initial position and the final position like that. Yes, it was here, but what is the gain in the height? So this is the distance that you use. So this distance is associated with, if you have the angle 30 here, degrees, then you have 5 meters. Without wasting time, just look at the opposite side is associated with sine. So you are going to say whatever distance you have, d, whatever distance you have, which is your d, then you are just going to say the sine, because sine is associated with the opposite sine of that angle theta. So that is, so this distance, the height, is d sine of 30. Why is it that? Because this angle is opposite to this side. So we are going to have times our height, which is 5, then 5, you are going to say the sine of 30 degrees. Like this. So this is basically how we answer that. So with that said, we are going to have our 1037.82, which should be equal to, we have our half by 10 is 5 v final squared, then we have minus half by 10 by 9 squared. This gives us, so 0.5 by 10 by 9, this gives us, and we have a 45 here like that. Then we are going to have plus our, if you multiply our 10 by 9.8 times 5 sine of 30, which should be equal to, we have 245 like that, 245 joules like that. So we are going to have the difference between that gives us, we are going to have so let me just move this a bit. So we have our 1037.82 should be equal to 5 VF squared. Negative 45 plus 45 will give us plus 200 joules like that. Then we move this the other side, it will be equal to, we are going to have, let me move this. So if we move this, we are going to have this 200 goes the other side, it will be 1037.82 minus 200 should be equal to 5 VF squared. So we are going to have our 1037.82 minus 200. This gives us a value that is equivalent to 837.82, which should be equal to 5 VF squared. We divide by 5, this gives us a value that is equivalent to, if we divide this by 5, it will be equal to 167.564, which should be equal to VF squared. We find the roots, so the root of this one will give us a value of 12.94, should be equal to velocity final. So this is our velocity in meters per second. So either you use that or this. So if we have the second question, which is saying that a block of mass 2 kg is put down a rough plane of inclination 37 degrees with a constant force of 20 newtons acting parallel to the incline. If it is found that the block moves on the incline with an acceleration of 10 meters per second, the block started from rest after 1 second, find the work done by the applied force. the normal force and the weight of the block, the frictional force. So firstly, the work done. So let's draw something. So we have the incline like that. Now for this incline, we have the mass of the block here. Then it is going down according to what we have been told. We have been told that a block of mass 2 kg is pushed down a rough inclined plane of 37 with a constant force of 20 newtons. So it is like that. So this is the force like that. So we are going to have 37 degrees there. We are going to distribute this into its components. This one will be our mg cos of our theta. This one will be the normal force like that. There will always be a force that will be acting downwards, which is the mg sine of our theta like that. Then is this down a rough, meaning to say friction is there. If it is going down, it means to say friction has to be in the opposite side like that. So this is the frictional force like that. So after doing all this, is there anything more? We can also add the mg there. So after doing all this, the work done by the force applied, we are going to have the work by the force should be equal to the product of the force times the distance times the cosine of theta. Remember what I said, this cosine of theta is not this one. This is associated with what is the relationship with how it's moving and the angle of inclination. We are told that it is pulled with a constant force of 20 newtons acting parallel to the incline. So if it is acting parallel to the incline, it means to say the angle between that force and the incline is 0. So this will be a 0 there. So we are going to have force times the d cos of 0, and cos of 0 degrees is 1. Now this force, which is parallel, it is not at an angle. We have it is 20 newtons, so we are going to say 20 newtons times the distance it is to move. We are told that the distance is equivalent to, we told the distance, a block of mass this down the incline with a constant force F parallel to this. So we are not given the distance, but we can find it, provided that they have given us that it takes 1 second, finds the work done. So we can find, using kinematic equations, S is equal to ut plus our half at squared. We also have the v squared. Mostly it's these that will work. V squared is equal to u squared plus 2as. Now ask yourself, what do I have? I have time, it's 1 second. I also have the initial speed, which is, I have the acceleration, not the initial speed. Then we are told that a mass pushed down, it is found that the block moves with an acceleration. The block started from rest, so I have initial. So I'll use this one because I have everything. I have initial, time, I have acceleration. So my S should be equal to, the initial is 0 since it started at rest, by the time, which is 1. Then we have plus our half, our acceleration is 10 meters per second. Then we have times our time, which is 1, like that. So our S is equal to, this is 0, half by 5, half by 10 will give us 5 meters. So that distance is 5 meters. The lamp is 5 meters. So from here to here, we have 5 meters like that. So we have the 5 meters. Then what we are going to have is, we know that the cos of 0 degrees is 1. So we can even put 1. 20 by 5 will give us 100 joules, like that. So that is basically how we are going to find the work done by the force, like that. The second part of the question says the work done by the normal. Remember, the work done is the product of the force and the distance moved in the direction of the force. Now, if you look at the normal force, this one is moving down. It is moving down like that. So therefore, the work done by the normal is equal to 0, unless if it was acting like if the block was being moved from the lamp like that, then we can have the work done by the normal force, because if contact is maintained, it means to say there is no distance moved in the direction of the normal force. So we can be able to say the work done by the normal force is equal to 0 joules. This 100 joules, the other one 0 joules, simply because it is not moving in the direction of the applied force, which is the normal force. The work done by the weight, so the work done by the weight is the same as the work done by the gravity. It is equal to the work done by the weight. So how do we find that? So the one that is pushing it down, if you recall, so as we can see, the one that is pushing it down is the mg sine of our theta, like that. So this force is the one that is associated with gravity, because gravity pulls things down. So we are going to have the mg, so we have the force is mg sine of theta times the distance moved, which is the distance of the lamp. So we are going to have our mg, which is equal to, let's move this, our 2 kg. So first, let's put it here. We are going to have our 2 kg by our 9.8 times the sine of the angle of inclination, which is 37 degrees, times the distance. What is our distance? So our distance for this problem is equal to, we found it to be 5. So the distance of the lamp is 5. So we are going to have our value, which is our 2 times 9.8 times 9.8 sine of 37 degrees. Then we are going to multiply by 5. This gives us a value of 58.98 joules. So this is the work done by the weight. So this is our work done by the weight. Then the next one is saying that the work done by the friction. So the work done by the friction is equal to the product of the frictional force times the distance times the cosine of 180 degrees. So we are going to have our work done by the frictional force. Frictional force first is equal to the coefficient of kinetic friction times the normal force. If the normal force in this case, remember the lamp is like this. We have the normal force like that. Then opposite the normal force, the one that is acting in the opposite direction is the mg cos of theta. So where there is the normal force, you can put mg cos of theta, or rather, using Newton's second law, summation of forces in the y, it is not moving in the y direction in terms of it is keeping contact, so it is equal to 0. We are going to say what force is there, for the normal force minus the mg cos of theta, they are acting in opposite direction, should be equal to 0. So the normal force should be equal to, if this goes this side, it will be mg cos of theta, like that. So our normal force will be equal to, our mass is 2 kg by our 9.8 times the cos of 37 degrees. This gives us a value of, so we have 2 by 9.8 cosine of 37. This gives us a value of 15.65 newtons. So this is the normal force, knowing that the frictional force will be equal to mu k if it's moving times the normal force. So we are going to have the mu k, which is equal to, we have the 20, where's the mu k? Do we have, okay, so since we don't have the frictional force, let's do something. What do they want us to find? They want us to find the work done by the frictional force. They haven't given us that force. So we can be able to say the net work done is equal to, not the change in the kinetic energy. We are not going, let's just find the net work done. So the net work done is, if you add the work done by the gravity plus the work done by the normal force plus the work done by a force plus the work done by the frictional force, like that. So in this formula, there is nothing like work done by the potential energy. No, these are the ones that we are going to be using. So the work done by gravity, it was found to be equal to, which is the work done by the weight, which is 58.98, 58.98, like that. Then we have our normal force, which is 0, plus our force. The force was applying, the work done by the force was found to be 100 joules. So we can be able to say 100 joules. Then we have plus the friction, the work done by the friction, which we don't know. So this is the net work. But remember, the net work done should be equal to the change in the kinetic energy, which is according to the Work-Energy Theorem. So we are going to have the net work done. We have our half, then we have our mass velocity final squared minus half the mass velocity initial squared. Then we are going to have our, we are going to replace what is our net work done. So remember, the net work done in this case is equivalent to, we have our 58, so the net work done is equal to this. So we have 58.98 plus joules plus 100 joules plus our work done by the frictional force. So if we add this, we are going to have 58.98 plus 100, it will be 158.98 joules plus the work done by the frictional force, which would be equal to, we have half by the mass, which is equivalent to 2 kg. So we are going to put our 2 kg there. In fact, we can even factorize this so that we even save space. Half is common, mass is common, then we have V final squared minus V initial squared, like that. So this gives us 158.98 plus the work done by the friction, which should be equal to half. The mass is 2 kg by the velocity final, which should be equal to, the final velocity is so we are told, where is it going? Pushed down. So we have it is being pushed down, so we need to find the velocity in that case. So the velocity, using the kinematic equation, SUT plus half AT squared, we have V squared should be equal to U squared plus 2AS. So provided that 2AS, we know the distance, we can use this formula. We know the distance, we know the acceleration, we know the initial, it started from rest. But in this case, since we can also use this equation, so anyone who uses this, the answer will be the same. So the velocity should be equal to, initial is 0 meters per second, then we have, since it started at rest, plus the acceleration is 10 meters per second, then we have our time is 1, so the V should be equal to 10 meters per seconds like that. So taking that into account, we are going to put our velocity final, which is our 10 meters per second. Then we have we square this, then we have minus the initial is 0 squared like that. So this gives us a value that is equivalent to we are going to have 158.98 plus the work done by the friction should be equal to half by this and this will cancel. Then 10 squared will be equal to 100 like that. So then this will go this side. So the work done by the friction should be equal to 100 minus 158.98 like that. So the work done by the friction should be equal to negative 58.98 joules. It is even given as negative, which makes sense. So let's move on to our next problem. We have this one. We are told starting from rest, a 5 kg block slides 2.5 meters down a rough 30 degrees incline. The coefficient of kinetic friction between the block and the inclination is mu should be equal to 0.4. Find the work done by the gravity. So we have first, let's draw what we have. We have something like this. So it is sliding down the rough incline. So it is here, then it is going down. So there is a force. Is there a force applied here? We have down an incline starting from rest. So there is no force being applied. So it is just the one that is causing it to go down is this one, which is our mg sine of our theta. The normal force pointing up. Then down here we are going to have our mg cos of our theta like that. Then this other side it will be the frictional force since it is going down like that. So that is basically what we need. So we have our mg like that. So that is what we have. So just moving it like that. So this is what we have there. So the work done by gravity, remember the work done by the gravity should be equal to the force. The force, we know that the force for the work done by gravity is the mg sine of theta, mg sine of our theta times the distance, which is the distance of the lamp. So that we are going to have our mg, our m is equal to 5, so we are going to say 5 by 9.8 times the sine of the angle is equal to, we have 30 degrees, so we are going to say 30 degrees times the distance, which is our 2.5 if I'm not mistaken. So if it is going down, the work done by gravity is positive because it's going down. So the work done by gravity is equal to that. So we can multiply 5 times our 9.8, times our the sine of 30 times our 2.5. This gives us a value that is equivalent to the work done by the gravity should be equal to, we have 61.25 joules like that. So we get our 3 marks there. Then here the work done by the frictional force between the block and the incline. So the work done by the frictional force between the block and the incline, we are going to have the work done by the friction should be equal to, we are going to say the force, the frictional force times the distance with the cosine of 180 degrees. We have explained why we use the cosine of 180. It is occurring in the opposite direction. So therefore, what are we going to have? So we have the frictional force is equal to the coefficient of kinetic friction times the normal force. So remember, it is like this. So the incline is like this. We have the normal force there. Then opposite the normal force is your mg cosine of our theta. So the frictional force is equal to, so we are going to have, let's find our normal force. We are going to have the summation of forces in the y is equal to 0. It is not leaving the contact. It will be the normal force minus, so we have minus the opposite force, which is our mg sine of our, not sine but cos of our theta, should be equal to 0. The normal force should be equal to, if this goes this side, it will be mg cos of our theta, like that. So the normal force should be equal to, what is our mass? This gives us the mass. What is our mass? We have 5 kg, so we can say 5 by 9.8, 5 kg by 9.8 newtons per kg. Then we are going to have, by our cosine of what is our angle of inclination, it's 30 degrees. So we can be able to say 30 degrees. So the normal force should be equal to, we have 5 by 9.8 by the cosine of 30, which gives us a value of 42.44 joules. So after we have done that, we can now calculate to say the frictional force is equal to the coefficient of kinetic friction times the normal force. So the mu k is equal to 0.4, so we can put it there. So we have our 0.4 by 42.44 joules, which gives us, by our 0.4, this gives us our 16.974, like that, joules. So this is our frictional force. Therefore, the work done by friction is equal to the frictional force by the distance times the cosine of 180 degrees. So the frictional force will be 16.974 by the distance. What is our distance in this case? So the distance that it moves is 2.5. So we are going to put it there. 2.5 by the cosine of what is 180 degrees. This gives us, if we multiply 2.5, we are going to have our negative 42, because of the cos of 180, 42.44 joules. So that is the work done by the friction. Let's hope I didn't mess up here the units. This is a force, so Newton, like that. So this is our frictional force. So looking at this other one, we have the final velocity at the bottom of the incline. So we are going to solve it in two ways. Remember, we have two formulas which we can be able to use, in which we are going to say the net work done according to the Work-Energy Theorem should be equal to the change in the kinetic energy. So the net work done, remember, this will be the work done by gravity plus the work done by the normal plus the work done by a force, if any, but there's no force. So we have the work done by the friction, like that. So this will be equal to, plus the work done by the force should be equal to the kinetic energy. The change will be half mv final squared minus half mv initial squared, like that. So in this case, we have the work done by gravity is equivalent to negative 42.44 joules, plus the work done by the normal, it is not leaving contact, so it's 0 joules, plus the work done by the friction. So this is not the work done by gravity. Work done by gravity was found to be 61.25. So 61.25 61.25 plus the work done by the friction now is equal to negative 42.44 joules plus the work done by the friction, or the force, it is not there, so it's 0 joules, should be equal to, we are going to say, so just moving this a bit, so this force should be equal to, we have half, we can factorize this, so half and m is common, v final squared minus v initial squared, like that. So we have 61.25 minus 61.25 minus the 42.44. This gives us a value that is equivalent to 18.81 joules, which should be equal to half. Then the mass is equivalent to 5 kg, so we can have 5 kg by the v final is unknown, minus the initial velocity is equivalent, it is starting from rest, so it's 0, so we have 0 meters per second. So this gives us half by 0.5 by 5, this gives us 2.5, so we are going to have 2.5. Then in the brackets we have v final squared minus 0 will be v final squared. Then we have 18.81 joules. We divide the 2.5, we divide by the 2.5, we are going to have our v final squared is equal to 18.81 over 2.5. So we are going to find the square root. So v final should be equal to, we have 18.81 divided by our answer. This gives us a value of 7. So the square root of everything inside is giving us, the root of this one will give us a 2.742, like that. Even 3 is okay. Meters per, in fact this is 3 meters per second. So this is our final velocity. Alternatively, you can use the conservation of mechanical energy, which is the work done by a non-conservative force, which is NC, should be equal to the change in the mechanical energy, of which we know that this will be the change in the kinetic energy plus the change in the potential energy, like that. So the work done by a non-conservative force will be equal to that. Now in this case, if there is no force, the only non-conservative force here will be the work done by the friction, which should be equal to, the kinetic energy can be split in two. We are going to have the kinetic energy final minus the kinetic energy initial should be equal to we have plus the potential energy final minus the potential energy initial. Now remember, this one is sliding down, so meaning to say the initial potential energy is there, but the final potential energy is not there. Why is that? Because at the top potential energy is there, but when it is here, the height h is equal to 0. Therefore, whatever you say mgh, if h is 0, it means to say even this whole thing becomes a 0. So therefore, what are we going to do? So we are going to say the work done by a non-conservative, the friction in this case, should be equal to the kinetic energy final minus the 0, because it started from rest. If there is no speed, there is no kinetic energy, plus the potential energy is also 0. Why? Because the potential energy is equal to 0 simply because at the end, at the tip there, it was we have what can I say, the height is 0, therefore the potential energy is 0. So we have minus the potential energy initial. So the work done by the non-conservative force becomes the kinetic energy final minus the potential energy initial, which will be, so we have the work done by the friction should be equal to half. This is the kinetic energy final, so we have half mv final squared. Then we have minus, this one is our mg, the initial height, like that. Now this height, remember, it is the vertical height. The vertical height from here to here. Now this height, if you have the angle, which is our 30 degrees, if I'm not mistaken, if we have our angle of 30 degrees, it means to say this angle, this distance will just be that, the distance of the lamp, then attach the sine, because sine is associated with opposite, sine of the angle 30 degrees. So that is the value of our h, is the sine of our 30 degrees. So replacing the work done by the frictional force in this question was a negative 42.44, like that. Joules should be equal to, we have our half mass velocity final squared, or we can replace by our mass, which is equivalent to, let's move this so that we don't go back. So looking at this, we have what do we have? Our mass, which is 5 kg, by our velocity final, which we don't know. Then we are going to have minus our mass, which is 5 kg, by the 9.8. So we are using this 9.8 by the distance, which is d sine of 30. So the distance of the lamp is 2.5. So we are going to say by 2.5, then the sine of our 30 degrees. So we are going to have negative 42.44 joules should be equal to half by 5 is 2.5 v final squared, minus, if we multiply 5 by 9.8 by 2.5 sine over 30, this gives us a value of 61.25 joules. So we are going to have this, when it goes this side, it will be negative 42.44 joules, plus, if this value goes this side, plus our 61.25 joules should be equal to, we have 2.5 v final squared. If we add our negative 42 plus our 65 or 61.25, this gives us, so we have 61.25 minus 42.44, this gives us a value of 18.81, should be equal to 2.5 v final squared. We divide the 2.5, we divide the 2.5, our value becomes our 18.81 over 2.5 should be equal to v final squared. So whichever one is easier for you. So we are going to have our 18.81 divided by 2.5. This gives us a value of the root of this gives us a value of 2.743 meters per second, which should be equal to Vf, like that. So this is basically how we do that one. So let's look at our last question. A 2 kg block of starts to slide up a 20 degrees incline with an initial speed of this. It stops after sliding 37 and slides back down, assuming that the frictional force impeding its motion to be constant. How large is the frictional force? So we have something like this. So this block is starting at the bottom, then it is going up. So let's quickly split. We have the Fn. Down here we have the mg cos of theta. Downwards, this force will always be acting downwards. We have the mg
sine of our theta, like that. Then if we are moving up there, the frictional force should also be moving in this direction. So we are told that it slides up like that. So the angle is, we are told that the angle is 20 degrees. So we can put the angle here, 20 degrees. So we are told the first one is when it goes up, we are told that to assume that the frictional force going up. So when it is going up, the frictional force is down. Then when it reaches that height, it slides back down. So when it is here, we are told to assume that even here, the frictional force is constant, but just pointing in the opposite direction. Here it is pointing down, here it is pointing up, but assume that the frictional force impending its motion is constant, like that. So what are we going to do? So since we have been asked the force, we don't have the coefficient of kinetic friction, we are going to say the net work done should be equal to, we are going to say the change, not the net work done, but let's use the work done by a non-conservative force. Work done by a non-conservative force should be equal to the change in the mechanical energy, which can be the work done by the non-conservative force. In this case, if there is no other force, then this work will be the work by friction, should be equal to the work done by the kinetic energy plus the change in the potential energy, which will give us, here we know that this is our half mv final squared minus half mv initial squared. Then we have plus our final is mg height final squared, or just this. Then we have, okay, let's eliminate some things. Let's eliminate some things before we complicate things. We have kinetic energy final minus kinetic energy initial. Then we have plus potential energy final minus potential energy initial. So we have the work done by the friction. So the work done by the friction there will be equal to, so remember it is starts to slide up with an initial speed of 200. So meaning to say there is an initial speed. It stops after 37 centimeters. So if it stops, the final is 0. So we can have 0 there, 0 meters per second minus the kinetic energy initial, like that. Then we have the potential energy final is there. So we are going to have plus our potential energy final, like that. So this is basically what we have. So we are going to now replace. We know that the work done by the friction, so we have the work done by the friction is equal to negative kinetic energy initial plus the potential energy final, which will give us the work done by the friction should be equal to the frictional force by the distance times the cosine of 180 degrees, like that. So we are looking for the frictional force, so we are just going to replace it like this without necessarily substituting some things. So we are going to have the frictional force times the distance times the cosine of 180 degrees should be equal to negative 1/2 mv. So if it's initial, it will be initial squared, like that. Then we have plus our potential energy, which is our mgh final, like that. So now let's replace things. So we have, let's convert 200 centimeters per second is just 200 centimeters over 1 second. So this, to convert this, you are going to multiply using the chain link conversion. The centimeter is up here, so meaning to say you are going to put the centimeters down, and we know that in 1 meter there are 100 centimeters. So we are going to cancel this. Then we are going to have 2 times 1 meter, it will be 2 meters per second, like that. So that is the speed, the initial speed. Then also 37 centimeters is equal to, you just divide 100 to convert to meters. So we are going to have 0.37 meters like that. So with that said, we can now use this equation, but just be careful of the height. I believe now you are conversant with the height we are going to be using. So we have the frictional force by the distance, which is our 0.37, by the cosine of 180 degrees should be equal to negative 1/2 by the mass, which is equivalent to, the mass is equivalent to 2 kg. So we are going to put the 2 kg by the initial velocity, which is our 2 squared. Then we have plus, what is our mass? It's 2 kg. Then we have our 9.8 times the height final. So the height in this case, remember, it is the potential energy. As long as you are dealing with the potential energy, you are going to be dealing with the sine of the angle. So in this case, the angle is what? Is it 20? It's 20, not 30. So you are going to say times the height, which will be the distance. The distance in this case is 0.37, which is the distance of the lamp. We have 0.37 meters. Then we are going to say by the sine of the angle there, the angle of inclination is 20 degrees, which will give us, cos of this will be a negative. So we have negative f by 0.37. Then we have this and this cancels. Negative by that, we are going to have negative 4 like that. Then we have plus our 2 by 9.8 by 0.37 sine of 20. This gives us a value that is equivalent to 2.48 like that. So this 2.48, we are going to add it, negative 4 minus negative 4. This gives us a negative 1.552 like that. Negative f by 0.37. We divide the negative 0.37. We divide the 0.37, which will give us a value that is equivalent to, the frictional force is equal to, divided by 0.37. This gives us a positive 4.11 newtons like that. So this is how you find the frictional force in that regard. Then the last part, which is what speed as it reaches the bottom. So what is our speed as it reaches the bottom? So the speed, so let's use the net work according to the Work-Energy Theorem is equal to the change in the kinetic energy, which will give us our half mv final squared minus half mv initial squared. So what do we have here? We have the net work is the work done by the gravity plus the work done by friction plus the work done by the normal plus the work done by a force, if any. So without wasting time, we now know how to find the work done by the gravity. So we are told that what is the work done, or what is at what speed as it reaches the bottom. So as it reaches the bottom, it is going down, meaning to say the work done by gravity is positive. And the work done by gravity, if you recall, it's mg sine of theta times the distance. Then we have the work done by the friction, which is plus the frictional force times So the work done by friction is frictional force times the d cos of 180 degrees. The work done by the normal is 0. We don't have any force there. Then the final velocity, we don't know, so we have half by the mass, which is our 2 kg, by v final squared, plus the initial is 0. If you look at it from the perspective of when it is at the top there, it stopped at that mark before it started to slide. So the initial from the top going down, the initial is 0, like that. So that's how come I say 0 there. So my mass will be equal to, we have 2 by the 9.8 by the sine of 20 degrees by the distance, which is the 0.37, that's the distance of the lamp. Then we have plus the frictional force, we found it to be 4.11. I'm a bit fast. So we have times the distance, which is 0.37 by the cos of 180 degrees. So reducing this a bit, we are going to have this and this cancels. We have the v final squared, which will be the 2 times 9.8, the sine of 20, then that will give us 6.7 by 0.37. This gives us a positive 2.48. Then we have minus, because cos of 180 is negative, so we have 4.11 by 0.37. It will give us a minus 1.5207, which will be equal to v final squared. So subtracting those two, 2.48 minus 1.5207, this will give us a 0.9593, which will be equal to v final squared. To find the speed, we find the root. We have v final, which should be equal to, so if we find the square root of this will give us a 0.98 meters per second. So that is how we deal with work on an incline. Thank you very much for watching. Hope you would like, subscribe, and share for more. See you in the next tutorial.